Hi everyone, this is Dr. Saida Falafini from Cal Poly Pomona. In this video, we are going to talk about exponential queuing systems in series. In every queuing system that we looked at so far, there were one operation that had to perform in the system. Either we had only one server that had to perform that operation, or we had multiple servers that were working in parallel. But anyway, the entity would go under just one operation. And in the queuing system in series, we are looking at the scenarios when the entities come to the system, for example, and then they can go get the first operation on a bunch of parallel locations, which are all of them are performing, let's say, stage one. And then so the cars go to any one of these, and then when they are done, the entities go to any one of these machines or any one of these servers, and when they are done, the entities again stay in the line for the second operation. And we may have a bunch of parallel machines that perform the second operation. So I call it stage 2 operation. And so the entities go to the second stage operation. When they are done, they come out, they go to the third operation, to the fourth operation, all the way till they are finally in the line to get the last operation done. And again, for the last operation, I may have a bunch of the servers that are working in parallel. And let's say the whole production process has K stage. So this is the stage K operation then. And then the entities go to the last stage operation, and when they are done, then they leave the system. We assume that in stage 1, the servers work with the service rate mu1. In stage 2, servers work with the service rate mu2. In stage K, servers work with the service rate mu-k. And like always, these rates of service are basically the rate of service for each one of these machines. So the rate of service of each one of these machines in stage 1 is mu1. It's the rate of service of each one of these servers in stage 2 is mu2, and so forth. So basically that's what we mean with queuing system in series. So each one of these systems basically is like a queuing system which we have looked at so far, right? So now we have a bunch of queuing systems that are one after another. They're queuing system in series. And here is the general scenario when every stage has multiple servers. This is not necessarily the case. So we may have in the stage 1, you may have only one machine, one server that is performing operations, and then you go to stage 2, you may have 3 machines that are working or performing the operations, and then so far in every stage the number of servers that you have is different. It can vary from 1 all the way to any number that you want. So but the basically diagram that you see here is a general scenario where each stage can have as many machines as possible. So in these systems, we call this K stage series queuing system, or a tandem queuing system. Okay, so that's what we call. To be able to analyze this queuing system, there is a theorem that can help us. And in this theorem, it says that if 3 condition holds, the first condition is that the interarrival times have exponential distribution. The interarrival time has exponential distribution with rate lambda, and the interarrival time is here, right? The arrival of entities to the system. So that's where this arrival happens, the arrival of the entities to the system. If it has the interarrival time has exponential distribution with rate lambda, that's the first condition. The second condition, if the service times at each stage has exponential distribution as well. Obviously, the service times can be different from each other at each stage, but all of them have to have exponential distribution. If that condition also holds, and the third condition, each stage has infinite capacity in the waiting room or has infinite area in the waiting room. And when I say waiting room, I mean these queues here. So that's what I mean. So the waiting room here, the waiting room here, the waiting room here. So we assume that these waiting rooms between these stages has infinite capacity, so they can hold as many entities as we receive from previous stage. Okay, so when this stage is done, they send the entities to this waiting room and they are waiting for to get processed on the next stage and so forth. We assume these waiting areas have capacity of infinite. They can hold as many entities as we want. So if these three conditions hold, two things can be concluded. Each stage on this queuing system can be treated as a independent queuing system, which is MMS, arrival rate lambda. Basically what this says is that if these three conditions hold, if inter-arrival time to this system have exponential distribution, so the entities arrive to this whole queuing system with the rate of lambda. If the service time on each one of these stages has exponential distribution and mu j is the service rate of each one of the machines in that stage. And if these waiting areas have capacity of infinity, then we can treat each one of these stages as a separate queuing system and we can analyze them independently. So then stage one would be a queuing system on its own, stage two will be a queuing system on its own, stage three and then all the way to stage K will be a queuing system, a separate queuing system on its own. We can model and analyze each one of them separately. In these queuing systems, the arrival rate for each one of them will be lambda. So the same lambda, which was the arrival rate for the whole system, now is the arrival rate for each one of these queuing systems that we are going to analyze separately. So the arrival rate to each one of these queuing systems will be lambda, and the service rates for each one of the machines in these queuing systems that are working in parallel will be mu k, mu j, I mean mu1 or mu2 or mu k, depending on which stage we are looking at. So that's basically what it means. Each stage of this queuing system can be treated as an MMS. It's J because basically we are talking about stage J. It has J servers. So each one of them can be treated as a separate independent MMS system with the arrival rate of lambda, which was the arrival rate to the whole system, and the service rate for each one of the machines or servers in that stage will be mu j, which is the service rate of each one of the machines in the stage J. And we know how we analyze each one of these separate queuing systems or independent queuing system, right? You know how to analyze MM1, MMS, or any type of queuing system that they may be, because that's what we learned all the way so far. We learned how to analyze queuing systems when there is only one operation. We may have multiple machines right here to perform that one operation, and that's fine, but there is one operation. So then we just treat each one of these stages as a separate queuing system and we just add everything that we want. If you are modeling a queuing system like this, and if I ask you that, for example, what is L, average number of entities in the system, then you have to calculate L1, which is number of entities in a stage 1, number of entities in a stage 2, all the way to number of entities in a stage K of the operation, and just add all of them together, and that tells me what is the average number of entities in this whole queuing system. And when I say in this whole queuing system, I mean the whole queuing system in series. If I ask you what is the time waiting in the system, you calculate the waiting time in stage 1, in stage 2, all the way to stage K. And similarly, if I calculate about ask about LQ, WQ, and everything, you can do that. And I want to go over one example. In this example, we are talking about a car manufacturing company. In this car manufacturing company, the last two operations are installing the engine and putting on the tires. Okay, so these two operations are done after each other, one after each other. So these are the two operations that are done in series. On average, 50 cars per hour arrive requiring these two tasks. Okay, so that's the number of cars that come to the system to get these two tasks per hour. One worker installs engine and he can provide service on average to 60 cars per hour. Okay, so there is in the first operation, and there is one worker who is working for the engine installation, and this worker can provide service to 60 cars per hour. So mu 1, I would say for stage 1 is 60 cars per hour. And then the cars go to stage 2, which is tire installation. And there are 3 workers at in the tire installation station who are doing the tire installation. And each worker at tire installation takes 3 minutes to put the tires on each car. All the tires, all 4. So what is given to you here? Each worker at the tire installation station takes 3 minutes to put the tires on each car. So then service rate, I'm going to call it mu2 for stage 2. Service rate is going to be 1/3 car per minute. And I can multiply it by 60 minutes per hour. So that's going to be 20 cars per hour. So that's the service rate of each one of these workers. Inter-arrival times and service times have exponential distribution. Okay, we also learned here that on average 50 cars per hour arrive to the system requiring these services. So if this is our system, the rate of arrival to the system, or lambda, is also 50 cars, 54 cars per hour. Remember, there were 3 conditions that we had to check in queuing systems in series to see if we can model each one of them, each one of these stages as a separate queuing system. Do you remember what were those 3 conditions? The first condition was that if inter-arrival times of the customers or entities to the system has exponential distribution, which is the case here, that's what we mentioned here. If inter-arrival times have exponential distribution, if service times have exponential distributions, again, that's mentioned here.
And also,
if the waiting area, this area, where the entities are waiting for the second stage, or this area when the entities are waiting for the first stage operation, if the waiting areas have capacity of infinity, then we can treat each one of these stages as a separate queuing system, and then we can analyze them separately and independently. And with knowing the fact that the arrival rate to each one of these stages is going to be lambda. So the arrival rate to the queuing system will be the same for each one of these stages. And those 3 conditions hold here. Inter-arrival time has exponential distribution, service times have exponential distributions, and we assume the waiting areas have infinite capacity. There is no sentence here in the problem statement that there is limitation on the waiting areas. And so we assume that each one of these stages can be treated as a separate queuing system, and the arrival rate to each one of them is lambda. So if that's the case, then for stage 1, can you tell me what is the type of queuing system we are looking at for stage 1?
MM1.
That's MM1. The inter-arrival time has exponential distribution, service time has exponential distribution, and service number of servers is 1. So that's the very first basic queuing systems we learned. What I want to calculate here is the average queue length at each one of the stations. So what do I need to calculate here?
LQ.
Average queue length. Okay. So the formula for in MM1 system, so LQ for MM1 system, the formula was rho square over 1 minus rho, and rho is lambda over mu. Lambda here is 54. The service rate in a stage 1 is this information that we have here. 1 worker installs engines, and he can provide service to on average 60 cars per hour. So the service rate in stage 1, in the first stage, is 60, because there is 1 worker installing the engines. That's why we have as MM1 here. And this worker can provide service to 60 cars per hour. So the service rate at first stage is 60. Then if I put it 0.9 here, 1 minus 0.9, and that's going to be 8.1. What is the unit here? Cars. So that's the average queue length at the station 1. Now that we are here for station 1, let's also calculate WQ, which is the waiting time in the queue at the first station. That's going to be LQ over lambda, and that's going to be 8.1 divided by 54. And that's going to be 0.15 hours. That's the waiting queue in the stage 1. Let's go to stage 2. of the operation. What is the type of queuing systems in a queuing system in stage 2? It's an MM3. The inter-arrival times have exponential distributions, service times have exponential distributions, and there are 3 workers or 3 servers in that state. Okay, again, I need to calculate LQ, and we know the formula for LQ is probability of J greater than or equal to 3 or S, which is 3 here, rho over 1 minus rho. So I have to calculate rho. Can you tell me what is the formula for rho in an MMS system?
Lambda over S times mu.
Lambda over S mu. Lambda is 54 for each one of the stages. S is 3 and mu here is 20. And so the result again is 0.9, which again, as we want, is less than 1, so we are good. In the formula for LQ, I need to find probability of J greater than or equal to 3 from the table. So what are the 2 things I need to find this probability from the table?
Number of servers and rho.
Exactly, number of servers, S, which is 3, and rho, which is 0.9. And having these 2 numbers, the probability of J greater than or equal to 3 that we find from that table is 0.83. Multiplied by 0.9 over 1 minus 0.9, and that's 7.47 cars. And then WQ, the waiting time in the stage 2 is LQ divided by lambda, which is, so that gives me the waiting time in the stage 2, the waiting time in the queue for stage 2. So total waiting time for engine and tire installation. So WQ stage 1 plus WQ stage 2. So that would be the total waiting time in the system. If I ask you the total time they spend in the system, find W for stage 1, W for stage 2, add them together. Total number of cars in the system somewhere they're either waiting or being processed, find L for stage 1, L for stage 2, add them together, and so forth. Okay, so there's nothing really tricky about the queuing system in series. The only thing that you guys have to do is to realize that the problem context talks about the queuing system in series. Find the arrival rate to the system, find the service rate of each one of the stages, and the number of servers at each one of the stages, and also make sure those 3 conditions hold. If service times have exponential distribution, arrival times have inter-arrival times have exponential distributions, and there's infinite space between the stages. And usually if you don't, if the problem doesn't say anything about that part, just assume that that assumption holds. And then if that's the case, then you can treat each one of the stages as a separate queuing system, and the arrival rate for each one of these stages is lambda, which is the same arrival rate to the whole queuing system.